Before Max Planck ever changed physics, the world made sense in a comforting, mechanical way. Nature was assumed to be continuous, smooth, and infinitely divisible. Energy could flow in any amount, matter could be broken down endlessly, and equations behaved politely as long as you followed the rules of classical physics. By the late 19th century, this world, you felt complete. Many physicists believed the major discoveries were already done, and that the future of science would simply involve refining measurements and adding decimal places. It was in this atmosphere of confidence that a deep and embarrassing problem appeared, one that classical physics could not explain without collapsing into nonsense. The problem was heat. More specifically, it was the way hot objects emit light. When iron is heated, it glows red, then orange, then white. Experiments showed that every object emits radiation depending on its temperature, producing a precise curve of intensity versus frequency. Classical physics tried to explain this using well-established laws of electromagnetism and thermodynamics. The result was disastrous. The equations predicted that as frequency increased, the emitted energy would rise without limit. This meant that even a modestly warm object should release infinite energy at high frequencies. This prediction was so wrong that it earned a dramatic name, the ultraviolet catastrophe. Nature, clearly, was not behaving the way theory demanded. Max Planck was not a revolutionary thinker by temperament. He deeply respected classical physics and believed in deterministic laws. His goal was not to overthrow existing ideas, but to preserve them. He wanted to fix the equations, not rewrite reality. Planck worked relentlessly to find a classical explanation that would match experimental data. He tried every mathematical technique available, but nothing worked. The equations stubbornly diverged from reality. Eventually, backed into a corner, Planck made a move he later described as an act of desperation. He assumed that energy exchange between matter and radiation does not happen smoothly, but in discrete chunks. Instead of energy flowing continuously, it could only be absorbed or emitted in fixed packets proportional to frequency. This assumption had no physical justification at the time. It was not derived from known principles or supported by intuition. It was simply a mathematical trick that made the equations fit the data. When Planck introduced this assumption, the catastrophic infinities vanished. The curve matched reality perfectly. Out of this fix emerged a new constant, a tiny number that set the scale of these energy packets. What textbooks often fail to emphasize is that Planck did not believe this assumption described the real world. To him, quantization was a formal device, a way to get the right answer. He did not think energy itself was fundamentally discrete. In his own mind, classical continuity remained intact. Planck even resisted the interpretation that his constant represented a new law of nature. He hoped that one day, a deeper classical explanation would emerge and make this strange assumption unnecessary. But nature had other plans. When Albert Einstein studied Planck's formula, he took it seriously in a way Planck never intended. Einstein applied the idea of energy quanta to light itself and proposed that light sometimes behaves as if it is made of particles, later called photons. This was not a small extension. It was a radical claim that challenged the wave theory of light, one of the great triumphs of classical physics. Experiments soon confirmed Einstein's interpretation. The mathematical trick was revealing a deeper truth. This is where the first keynote becomes crucial. Planck's constant was not meant to describe reality. It was born as a patch, not a principle, and yet this patch cracked open the foundations of physics. The constant quietly embedded itself into every corner of the emerging quantum theory. It appeared in equations governing atoms, electrons, radiation, and eventually space and time themselves. What began as a numerical adjustment turned out to be a universal boundary marker. The unsettling implication is that one of the most fundamental constants of nature was discovered almost accidentally. There was no grand philosophical argument, no experimental hunt for discreteness. Instead, the universe forced the idea into existence by refusing to obey classical predictions. Planck's constant represents a moment when reality overruled human expectation. It marks the point where equations stopped being negotiable. Another detail often softened in textbooks is how violently this constant contradicts classical intuition. If Planck's constant were zero, the universe would behave exactly as classical physics predicts. Everything would be smooth, predictable, and continuous. The fact that it is not zero, even though it is extremely small, changes everything. It introduces a minimum scale of action, below which the classical concepts of trajectory, velocity, and even causality lose meaning. Planck's constant does not merely modify equations, it enforces limits. It tells us that nature refuses to reveal itself in arbitrarily fine detail. No matter how advanced our instruments become, there are combinations of quantities that cannot be known exactly at the same time. This is not a technological limitation, but a structural one. The universe is built with a resolution limit, and Planck's constant defines it. What is especially ironic is that Planck himself was deeply uncomfortable with where this led. As quantum mechanics developed, it embraced probability, uncertainty, and indeterminism. These ideas clashed with Planck's philosophical beliefs. He accepted the success of the theory, but remained uneasy about its interpretation. The constant that carried his name symbolized a universe less orderly than he had hoped. The documentary-style truth is that Planck's constant represents a fracture point in human understanding. Before it, physics aimed to describe what is. After it, physics was forced to accept limits on what can be described at all. The constant stands as evidence that nature is not obligated to align with human logic or preference. It operates according to rules that may feel unnatural, even disturbing, but are relentlessly precise. This first keynote also reveals something deeply human about scientific progress. Revolutions do not always arrive with confidence and clarity. Sometimes they emerge from reluctance, hesitation, and even denial. Planck did not set out to change the world. He was trying to save it from embarrassment. In doing so, he unknowingly exposed a deeper layer of reality that classical physics could never reach. The legacy of Planck's constant is therefore not just scientific, but philosophical. It teaches that the universe may hide its true structure behind mathematical necessity. When equations fail, it is not always because they are incomplete, but because our assumptions are wrong. Planck's constant exists because the universe demanded it, not because humans imagined it. As the 20th century unfolded, this constant became the cornerstone of quantum mechanics, appearing in Schrödinger's equation, Heisenberg's uncertainty principle, and every quantum field theory that followed. Its presence signals that we are no longer dealing with approximations of everyday experience, but with the raw architecture of existence. In the end, the most remarkable fact is not that Planck's constant changed physics, but that it did so against the will of its own creator. It reminds us that truth in science is not decided by intention or belief. Reality reveals itself when our theories fail, and sometimes the smallest constants carry the heaviest consequences. For centuries, The idea that the universe is smooth and continuous was not just a scientific assumption. It was a deeply held belief. Motion was imagined as flowing, space as infinitely divisible, and time as a perfect, unbroken stream. This belief felt so natural that it was rarely questioned. You could always zoom in further, cut things smaller, measure more precisely. From the swing of a pendulum to the orbit of planets, everything seemed to support this picture. Classical physics was built entirely on this foundation, and it worked astonishingly well for the human-scale world. The shock introduced by Planck's constant is that this smooth picture is not fundamental. It only works as an approximation. At deeper levels, the universe refuses to behave continuously. Instead of a flowing river, reality becomes more like a mosaic made of tiny tiles. You cannot divide energy endlessly. You cannot change action by arbitrarily small amounts. There is a smallest step, a minimum unit, and Planck's constant defines its size. What textbooks often gloss over is how disturbing this idea truly is. A continuous universe feels intuitive because our senses evolved in a world where Planck's constant is extremely small. We never notice the steps, but the fact that we do not notice them does not mean they are not there. Just as a digital image looks smooth from afar, but breaks into pixels when magnified, the universe hides its discreteness behind scale. This discreteness is not limited to energy alone. Once Planck's constant enters physics, it spreads everywhere. Atomic orbits are not smooth spirals but fixed states. Light is not just a wave filling space continuously, but arrives in indivisible packets. Even motion itself becomes constrained. A particle cannot have just any trajectory in the quantum world. Some paths are allowed, others forbidden, not because of forces, but because of quantization. The destruction of continuity is not gentle. It breaks classical logic in subtle but profound ways. In a continuous universe, knowing the present precisely means knowing the future exactly. This idea was central to classical determinism. If you know position and velocity perfectly, you can predict motion forever. Planck's constant quietly dismantles this assumption. Because quantities come in discrete units, perfect knowledge becomes impossible. The future is no longer a precise extension of the present. What is especially unsettling is that this discreteness is not a property of measurement, but of reality itself. Early attempts to dismiss quantum behavior blamed experimental imperfections. Better instruments, it was thought, would restore continuity. But Planck's constant makes this impossible. No improvement in technology can remove it. Even with perfect tools, nature does not allow arbitrarily fine distinctions. The universe itself has a built-in resolution. This idea forces a rethinking of space and time. While Planck's constant does not directly quantize space the way it quantizes energy, it strongly suggests that spacetime cannot be infinitely smooth either. Modern theories of quantum gravity take this implication seriously, proposing that space itself may have a granular structure at extremely small scales. The classical image of space as a smooth stage on which events unfold begins to look like a convenient illusion. The emotional resistance to this idea among early physicists was intense. Many found it deeply uncomfortable to abandon continuity. It felt like abandoning reason itself. Smoothness had always been associated with elegance and simplicity. Discreteness felt artificial, mechanical, almost ugly. Yet nature showed no interest in aesthetic preferences. Experiments repeatedly confirmed quantization, no matter how reluctantly theorists accepted it. One of the strangest consequences of abandoning continuity is the rise of probability as a fundamental concept. In a smooth universe, randomness is usually a sign of ignorance. If you don't know the details, outcomes appear random. In a quantized universe governed by Planck's constant, randomness is not just ignorance. It is built into the structure of reality. Even with complete information, only probabilities can be predicted. This is where the second keynote becomes unavoidable. Planck's constant quietly destroys the idea of a smooth, continuous universe. It does so not by dramatic announcement, but by persistent contradiction. Every attempt to preserve continuity fails at small scales. Every successful theory incorporates discreteness. The universe seems to insist on it. Another aspect rarely highlighted is how this discreteness protects stability. In a purely continuous universe, atoms would be unstable. Electrons would radiate energy continuously and collapse into nuclei. Matter itself would not exist in any lasting form. Quantization prevents this collapse by enforcing fixed energy levels. What feels like a limitation turns out to be a safeguard. The solidity of the world depends on the destruction of continuity. This realization flips intuition upside down. What we perceive as solid and stable emerges from a reality that is fragmented and constrained. Continuity is not fundamental, it is emergent. It arises only when vast numbers of quantum events average out. The smoothness we experience is a collective illusion produced by enormous scale, not a basic feature of existence. Planck's constant also forces a redefinition of what it means to observe motion. In classical physics, motion is a path through space over time. In quantum physics, motion becomes a sequence of allowed transitions. Particles do not slide continuously from one state to another, they jump. These jumps are not violent or dramatic, but they are real. The word quantum itself means a discrete amount, and Planck's constant is the ruler that measures it. This idea deeply unsettles everyday language. Words like between, halfway, and in the middle lose their meaning at fundamental scales. There is no halfway energy between two quantum states if that energy is not allowed. Reality becomes selective. It says yes to some possibilities and no to others without offering smooth transitions. Even time begins to feel different under this lens. While time is treated as continuous in standard quantum mechanics, Planck's constant links energy and time in such a way that extremely short time intervals become physically ambiguous. Events blur together. Cause and effect lose sharp boundaries. The classical notion of a precise moment becomes harder to defend. What textbooks often simplify is the philosophical cost of this shift. A continuous universe feels comprehensible. A quantized universe feels alien. It resists visualization. It replaces pictures with equations and intuition with abstraction. This is not a failure of imagination, but a reflection of reality's structure. The universe does not owe us mental comfort. Planck's constant also exposes the limits of reductionism. If reality were infinitely divisible, then understanding the smallest parts would automatically explain the whole. But with a minimum scale imposed, there is a point beyond which smaller stops making sense. You cannot endlessly peel layers of reality. At some point, the question itself becomes invalid. The destruction of continuity also changes how we think about causality. In classical physics, causes smoothly produce effects. In quantum physics, transitions happen probabilistically, constrained by discrete rules. The link between cause and effect becomes statistical rather than absolute. This does not mean causality disappears, but it becomes less rigid and more subtle. Perhaps the most profound implication is that continuity is revealed as a human convenience, not a cosmic truth. Our brains evolved to perceive smoothness because it works at our scale. Physics, guided by Planck's constant, reveals that this perception is not fundamental. It is a useful fiction. The second keynote, when fully understood, is not just about physics, but about humility. It tells us that the universe operates on principles that do not align with human expectation. Smoothness, elegance, and continuity are not guaranteed. Reality is structured, selective, and quantized, whether we like it or not. In the end, Planck's constant stands as a quiet demolisher of an ancient assumption. Without fanfare, it dismantles the idea that nature is infinitely divisible. It replaces a flowing universe with a stepped one, a continuous dream with a quantized reality. And once this is seen clearly, there is no going back. Long before quantum theory forced physicists to confront uncertainty, ignorance was treated as a temporary flaw. If something could not be measured precisely, the assumption was simple: the tools were not good enough. With better instruments, sharper eyes, and more refined methods, perfect knowledge seemed achievable in principle. Classical physics encouraged this confidence. Its equations suggested that the universe was an open book, written clearly, waiting only for careful reading. Planck's constant quietly ended that dream. What makes this shift so difficult to accept is that the limit it introduces is not practical, but fundamental. It does not matter how advanced technology becomes, or how clever experimental design grows. There are certain combinations of properties that nature itself will not allow us to know simultaneously with perfect precision. This is not because information is hidden, but because it does not exist in a perfectly defined form. Planck's constant defines the boundary of what can be known at all. This idea first became unavoidable through the behavior of microscopic particles. Electrons, photons, and atoms refused to behave like tiny billiard balls. Attempts to track their exact positions and velocities produced inconsistent results. The more precisely one quantity was measured, the more the other seemed to blur. At first, this was treated as a nuisance. Then it became a pattern. Eventually, it was formalized as a principle, with Planck's constant sitting at its core. What textbooks often present as a mathematical inequality is, in reality, a statement about the structure of existence. Planck's constant is the scale factor that turns uncertainty from an accident into a law. It says that the universe does not permit infinite informational density. There is a maximum amount of detail that can be packed into any physical situation. Beyond that, questions lose meaning. One of the most unsettling consequences of this limit is that it undermines the classical idea of trajectories. In the macroscopic world, objects follow paths. You can draw their motion as a line through space and time. In the quantum world, constrained by Planck's constant, such paths cannot be defined precisely. Particles do not travel along exact lines. They occupy ranges of possibility. Motion becomes a statistical concept rather than a geometric one. This limitation also applies to energy and time. Extremely short time intervals blur energy measurements, and precise energy definitions smear time. This is not a technical problem, but a built-in feature of reality. Planck's constant sets the conversion rate between time precision and energy precision, enforcing a trade-off that cannot be escaped. What makes this particularly disturbing is that it denies the observer a godlike perspective. Classical physics encouraged the idea that, at least in principle, An all-knowing observer could predict the future perfectly. Quantum physics removes this possibility. Even an observer with complete information about a system can only predict probabilities. Planck's constant ensures that certainty is not just difficult, but impossible. This is the heart of the third keynote. Planck's constant limits what nature allows us to know, measure, and predict. It draws a line not just around knowledge, but around existence itself. Some properties simply do not coexist in sharply defined forms. Asking for them simultaneously is like asking for a color that does not exist. The resistance to this idea was fierce. Einstein famously objected, insisting that the universe must be deterministic at some deeper level. He believed uncertainty reflected incomplete knowledge, not fundamental randomness. But experiment after experiment contradicted this hope. Nature behaved as if uncertainty was woven into its fabric. Planck's constant did not soften with better measurements. It stood firm. Another aspect rarely discussed outside deeper treatments is that this limit reshapes the meaning of objectivity. In classical physics, properties belong to objects independently of observation. In the quantum world, constrained by Planck's constant, properties often become relational. What can be said about a system depends on how it is measured. This does not mean reality is subjective, but it does mean it is not detached from interaction. The act of measurement itself becomes a physical process, not a passive observation. Because Planck's constant sets a minimum scale of action, measuring a system inevitably disturbs it. There is no way to extract information without interaction, and no interaction without consequence. This collapses the idea of perfectly non-invasive measurement. This leads to a profound shift in scientific humility. There are questions that sound reasonable but have no answers, not because we lack skill, but because the universe does not define them. Asking for both exact position and exact momentum is like asking for the exact shape of a wave and the exact location of a particle at the same time. The concepts themselves conflict at fundamental scales. Planck's constant also challenges the human desire for control. Prediction is power. The ability to forecast outcomes allows technology, engineering, and planning. Quantum limits do not remove this power, but they cap it. They say that prediction will always involve uncertainty. No system, no matter how simple, can be reduced to perfect foresight. Interestingly, this limitation does not make the universe chaotic. Quantum mechanics is extraordinarily precise in its statistical predictions. What Planck's constant forbids is certainty about individual events, not accuracy about ensembles. The universe is not lawless, it is probabilistic. Order exists, but it is a different kind of order than classical physics promised. Another subtle consequence is the redefinition of explanation itself. In classical science, explaining something often meant showing how it must happen. In quantum science, explanation often means showing why certain outcomes have certain probabilities. This shift is uncomfortable, especially for those who equate explanation with inevitability. What textbooks often underplay is how deeply this affects philosophy beyond physics. Concepts like free will, causation, and determinism are all touched by Planck's constant. If the universe is not strictly deterministic, then the future is not fully fixed by the past. This does not automatically grant freedom, but it does remove absolute predestination. Planck's constant also exposes the limits of reductionism in knowledge. If certain properties cannot be jointly defined, then complete descriptions are impossible. Any description involves choices about what to emphasize and what to blur. Knowledge becomes contextual, not absolute. Perhaps the most unsettling realization is that uncertainty is not a temporary stage on the road to deeper truth. It is the destination. Planck's constant does not point toward a future theory that will restore certainty. It defines a boundary that future theories must respect. Even more advanced frameworks incorporate it rather than eliminate it. This means that the universe is not fully transparent. There is a permanent haze at its foundations, not because nature is hiding, but because it is structured in a way that resists total clarity. This is not a failure of science, but one of its greatest revelations. The third keynote, when taken seriously, transforms the goal of physics. Instead of seeking perfect prediction, it seeks optimal understanding within limits. Instead of absolute certainty, it offers reliable probability. Instead of total control, it offers deep insight tempered by humility. In the end, Planck's constant stands as a reminder that knowledge has a shape, and that shape has edges. Beyond those edges, questions dissolve rather than receive answers. The universe allows understanding, but not omniscience. And that limit is not imposed by human weakness, but by reality itself. For most of human history, the world appeared unified under a single set of rules. The same logic that explained falling apples also described orbiting planets. Motion, force, and time behaved consistently across scales, at least as far as observation could reach. Classical physics gave the comforting impression that the universe was coherent in a simple way. Learn the laws, apply them everywhere, and reality would follow obediently. Planck's constant quietly exposed the limit of that confidence. What makes this limit so subtle is that it does not announce itself in everyday life. At human scales, Planck's constant is unimaginably small. Its effects are drowned out by mass, friction, and noise. Classical physics works not because it is fundamentally true, but because quantum effects average out. This creates the illusion of universality. Only when systems become small, cold, or isolated does the boundary begin to appear. That boundary is not a vague transition. It is sharp and mathematical. Planck's constant marks the exact point where classical intuition stops being reliable. Below this scale, concepts like definite position, continuous motion, and deterministic evolution begin to fail. They do not gradually weaken, they lose meaning altogether. The universe does not politely blur into quantum behavior. It switches frameworks. One of the most important consequences of this boundary is that classical explanations cannot be extended downward indefinitely. You cannot understand atoms by shrinking planetary models. You cannot explain electrons by imagining tiny balls orbiting smoothly. Every attempt to push classical pictures past the Planck boundary leads to contradictions. Energy diverges, stability disappears, and predictions break down. This is why Planck's constant is not just a number but a warning sign. It tells physicists when to stop trusting intuition and start trusting mathematics. Below this scale, pictures mislead, equations rule. The world becomes less about objects and more about relationships encoded in probability amplitudes. What textbooks often fail to emphasize is that this boundary runs both ways. Not only does classical physics fail at small scales, but quantum physics must reduce to classical behavior at large scales. Planck's constant controls this transition. When its influence becomes negligible compared to the scale of action involved, classical laws emerge naturally. This explains why everyday reality feels classical, even though it is built on quantum foundations. The fourth keynote lies here. Planck's constant marks the exact boundary where classical intuition fails. It is the switch that determines which description of reality applies. Without it, physics would be either entirely classical or entirely quantum, with no way to reconcile the two. With it, the universe gains a layered structure. This boundary also reshapes the meaning of explanation. In classical physics, explanation is often visual. You can draw diagrams, imagine forces, and trace motion. In quantum physics, explanation becomes abstract. It relies on wave, functions, operators, and probabilities. Planck's constant dictates when visualization stops working. It draws a line beyond which pictures lie. Another rarely discussed implication is that this boundary is observer and dependent. It does not care about human perception or technological capability. Even hypothetical observers with perfect instruments cannot bypass it. The failure of classical intuition is not a human failure. It is a structural feature of reality. This realization forced physicists to accept a pluralistic view of truth. Classical mechanics is not wrong, it is incomplete. Quantum mechanics is not strange, it is precise where classical ideas collapse. Planck's constant allows both to coexist, each valid within its domain. This layered truth is uncomfortable because it challenges the desire for a single, all-encompassing picture. The boundary also explains why analogies become dangerous. When classical metaphors are pushed too far, they produce confusion. Electrons are not little planets. Waves are not ripples in space like water. These images are scaffolding, useful at first, but misleading beyond a point. Planck's constant tells us when to remove them. One of the most profound consequences of this boundary is the reinterpretation of reality itself. At quantum scales, properties are not fixed attributes but potential outcomes. Classical intuition demands definite answers. Quantum reality offers distributions. Planck's constant enforces this shift. It ensures that certainty does not survive the crossing. This boundary is also responsible for some of the most counterintuitive phenomena ever observed. Tunneling, superposition, and entanglement all exist because classical restrictions dissolve below the Planck scale of action. What feels impossible from a classical perspective becomes natural in quantum terms. Planck's constant is the permission slip. Importantly, this boundary does not imply that quantum reality is more real than classical reality. Both are real within their domains. The mistake lies in assuming that one description must dominate all scales. Planck's constant prevents this dominance. It insists on contextual truth. Another subtle implication is the limit it places on reductionism. Even if you understand quantum rules perfectly, predicting macroscopic behavior remains complex. Classical simplicity does not automatically emerge from quantum detail in a straightforward way. The boundary is not just a scale transition, it is a conceptual one. Planck's constant also reframes the role of mathematics in physics. In classical physics, mathematics describes behavior that can often be visualized independently. In quantum physics, mathematics becomes the primary language of reality. Planck's constant sets the conversion factor between mathematical abstraction and physical effect. What is often underappreciated is how emotionally difficult this transition was for early physicists. Many resisted abandoning classical intuition because it felt like abandoning understanding itself, but the universe did not cooperate. Experiments consistently aligned with quantum predictions and violated classical expectations. Planck's constant stood at the center of this rebellion. The boundary it marks also shapes modern technology. Semiconductors, lasers, MRI machines, and quantum sensors all operate precisely because engineers respect where classical intuition fails. Ignoring this boundary would make modern technology impossible. On a deeper philosophical level, this boundary challenges realism. If classical concepts fail at fundamental scales, then reality cannot be fully captured by everyday categories. Planck's constant suggests that reality is richer than intuition, not poorer. In the end, the fourth keynote reveals that Planck's constant is a map legend for the universe. It does not tell us what the terrain looks like everywhere, but it tells us when our old maps stop working. Cross that boundary with classical intuition, and you get lost. Respect it, and a deeper, stranger, and more accurate picture of reality emerges. This constant stands as a reminder that understanding is scale, dependent. Truth changes its language as you move across the universe's layers. Planck's constant marks that change, not as an obstacle, but as a guide.